until the time you use it. Okay? Okay. So if we look at the actual code and we want to try and place process 2, then this is the part, the while loop that checks if the key already exists. That's the check part, okay? This is time of check, you see? This is the part where I actually check if the key already exists. And this is the time of use right there at the bottom. This is where I use the key that I just checked to see if, and this is where I use the key to create the object and save it to the database. So if we need to imagine what it looks like, then process 1 started with the check. And before it had a chance to move on to the last line, process 2 kicked in right here and ran the check and used the key to save the object to the database. And then when process 1 came back, tried to use the key, boom, we get a collision, okay? So normally, when we identify that we have a problem with concurrency or several processes operating at the same time on the same resource, then immediately our mind shifts to locks, right? So you say, if we have a problem with 2 processes competing over the same resource at the same time, then we must lock this resource, right? So when we reach the conclusion that we need to lock something, the next question would be, what should I actually lock? Okay, so to answer this question, we need to understand what an actual web application architecture looks like. Okay, so at the most basic level, you have usually, at least from the app that we just created, we have a database and we have a process. So Django, Flask, and a lot of other types of web frameworks usually use some kind of web server to respond and process requests from the web. So we have a database and we have a process that can accept requests and process them. So if this is our architecture and you want to lock, you might think, okay, so maybe I can just lock the process, okay, and avoid any collision like that. But usually web applications don't just run one process, they run multiple processes, right? You don't get a big server just to run one process. You want to be able to process multiple requests at the same time. So usually you would have multiple processes. In Django, for example, or any WSGI application, that would be worker processes. So if you have 2 worker processes, then you can no longer lock at the process level because you might get a collision happening in a different process. So at this point, you start thinking, okay, maybe something at the operating system level. I mean, these 2 processes run on the same server. So maybe there's something I can use on the server to obtain a lock, right? But actually, what if you have multiple servers running your web application? And that's actually very common. You can have multiple processes responding, multiple servers running multiple processes responding and processing requests from user. Okay, so at this point you can obtain a lock at the process level because you have multiple processes. You can obtain a lock at the operating system level because you have multiple servers. So you might think, okay, maybe I should do something at the application level. Maybe the application can produce some kind of locking mechanism that would enable me to prevent these types of issues from happening. But what if you actually have multiple applications operating on this resource? And if you think about it, it's not that far-fetched, because you might have a service that responds to API requests from users, and then you have another server or another application like a dashboard or an admin panel or some kind of internal systems that you use for support and operations. So it's not unlikely that you would have different applications hosted on different servers that interact with the same resources, okay? So at this point, hopefully it's clear that if we want to obtain a lock, we need to obtain a lock in the database, okay? Because this is where all the applications and all the processes and all the servers interact with. There's a single place where everything goes to, and that's the database, okay? So once we understand that we need to obtain a lock at the database level, the next question is, what do we need to lock? So we are trying to create a new show URL, a new resource. So this resource does not exist yet. So what can we actually lock? So the next thing that comes to mind is, okay, so I want to create a new row in a table, and I want to prevent concurrency issues from happening while I try to insert the row into the table. So maybe I should just lock the table, okay? So this is what it looks like if we want to try and lock the table. So first of all, if we want to obtain a lock, we need to do that inside a database transaction. This context processor in Django will essentially issue a begin statement to start a new transaction in the database, and then finish it off with commit at the end to commit the transaction. Okay, so if we want to obtain a lock, we first need to create a database transaction. And next, Django ORM does not provide any operations to lock tables. So we need to execute raw SQL. For that, we can create a cursor and execute this command, lock table, short URL in exclusive mod. This means that when we execute this statement, we try to obtain a lock on the table in exclusive mod, meaning only our process can obtain this lock, okay? So if we are unable to obtain the lock, it means that someone else locked the table. And if we do manage to get a lock on the table, it means that no other process is locking the table right now, and no other process can obtain a lock on the table until we're finished, okay? Until we finish the current transaction. So once we obtain a lock on the table, we can be sure that no one else is executing this piece of code at the same time. So by doing that, we know that no other process can go between the time of check and the time of use. So this will work, okay? This will work. This is a way to prevent concurrency issues. We lock the table to prevent concurrent processes from operating on it, okay? And we are not going to get collisions. We're not going to get integrity errors from this function. But we solved the TOCTOU problems, but now every other process that wants to create new URLs at the same time is forced to wait. This means that the process is now much slower, okay? If we have a big system that is used to handle big loads, we can't really have all the processes wait in line to create new resources, right? So we need a better solution. So the second solution, okay, the first one was to lock the table. The second solution is ask for forgiveness, okay? I know it sounds kind of funny, but so ask for forgiveness is actually a common Python coding style, okay, which says that it's easier to ask for forgiveness than permission. So what it means is that instead of checking things in advance, we go on and try to execute the operation and handle all the possible errors instead, okay? So if we go back to the model, okay, remember that we defined this key as unique. When we did that, Django, the ORM, behind the scenes, generated a unique constraint on this field in the database, okay? So what it means is that the database would not allow for duplicate values in this field, okay? So if the database already checks that key is unique, why not rely on? Why check in advance if the database is already checking this, right? So let's see what it looks like. So once again, we iterate, we run in a loop, we generate a random key, 5 digits long, 5 characters long. And then we try to create the short URL. And if we are unsuccessful, if we get an integrity error, if the database rejected our insert command because the key already exists, we just continue and we iterate again, okay? So we generate another key and try again. We generate another key and try again. So basically, we try different keys until we don't get an integrity error, okay? So this is a way of asking for forgiveness. Instead of checking in advance if the key exists in the database, we just handle the unique constraint violation if it happens, okay? So once the database is able to create the short URL, we can rest assured that the key is unique, okay? So I'm not going to go too deep into the special case here for Postgres, but I would just say that if you're using Postgres and you want to implement this pattern in your code, then you need to execute this inside a nested transaction. So there's an entire section in Django documentation that explains that. So I'm not going to get into that, but if you are using Postgres, then you need to add another transaction inside, okay? So by asking for forgiveness, we managed to solve our concurrency issue first without using a lock. So it's faster. We resolved our TOCTOU problem because we no longer check and then use. So there's no TOCTOU problem at all. And it's more Pythonic, right? Because asking for forgiveness is more Pythonic. And another benefit that we haven't discussed is that we now make less round trips to the database, right? Before we had to check and then we created the object. Now we just create the object. And if it doesn't fail, then we made just one round trip to the database to create the short URL, okay? So less round trips to the database. Great, so we solved the problem that we had creating the short URL. And now that we have short URLs in the database, we want to redirect and increment the hit counter. So once again, we start with a naive implementation. So this is what it looks like, a function that accepts a key, that's the random part at the end of the short URL, tries to find the short URL and redirect to that short URL. So this function resolves a key to a short URL and increments the hit counter, okay? So we try to fetch an object by the key, and then we increment the hit counter, save the object, and return it to the API layer so it can redirect to the long URL. So now that we are aware that there might be concurrency issues, we can ask ourselves, how would this behave if a lot of processes would try to resolve this the same URL at the same time. So the third mistake is ignoring race conditions. Let's see what a race condition can look like in this case. So process one tries to resolve the short URL, and at this point, the hit counter is 0. That's the initial value. Now, before process one has a chance to increment the value, process two tries to resolve the exact same key. Now, at this point, the hit counter is 0, right? Now, before process two has a chance to increment the hit counter, process one updates the hit counter. Now, it doesn't just increment because process one has the object. The current hits counter is 0. So process one updates the database that the hit counter is now 1, which is 0 plus 1, right? Now, the value of hits in the database is 1. But when process two wants to update the hit counter, it does the same thing. The current hit counts for process two is 0. So process two also issues an update command to set the hit counter to 1. Now, that's a problem because now the hit counter is incorrect, right? We had two processes trying to resolve the short URL, so it should be 2, but at the end of the process, the hit counter is 1. So that's incorrect. Now, if you have a URL shortener system and you actually charge by the number of hits, you're losing money here. So the problem here happens between the time we get the object, load the object from the database into memory until we actually increment the hit counter. So process one started with this, process two also started this, and then this is where another process kicks in. So this is called a race condition. Now, if we look at the generated URL, we can see that the first command fetches all the fields from short URL for a given key, okay? And then the second command that increments the hit counter sets the hit counter to an absolute value. That value is calculated by the application by taking the hit counter it fetched in the first line and sets it to +1, right? So the problem here can be solved by something called select for update, okay? So previously, we locked the table, but now we actually have a resource, we have a row. So what we can do is we can lock the row. Remember, every time we have a concurrency problem, we also always resort to locking. So there's a special clause in SQL called select for update. It essentially means that we want to fetch the row with the intent of updating it, okay, of changing it. So when we select for update, no other transaction can obtain the lock until we release the lock. So this is what it looks like. We start a transaction, database transaction, but now when we fetch the object, we say select for update. We are going to see what the SQL looks like in a second, okay? So select for update. At this point, we obtain a lock. So if another process is trying to do the same thing, it will fail because we locked the row. So once we manage to obtain a lock on the row, we can rest assured that this part is executed only by us, okay? So this is the change. Now we have a transaction, you see begin commit, and now the select includes a for update clause. This is how we tell the database that we want to fetch the row with the intent of updating it, okay? So we want to obtain a lock. So now this is safe. Another process cannot lock the row until this process is done, until we committed the transaction. So if we look at the same scenario again, process one fetch a row, hit counter is 0. Process two tries to get the row, but it is forced to wait. Process one updates the hit counter to 1 and commits the transaction, at which point the release is locked. The lock is released. Process two fetch a fresh copy of the row where the hit counter is updated to 1. increments to 2, and there you have it, 2 processes, and the hit counter is 2. Okay. So by using select for update, basically a lock again, we have an accurate counter, but once again, because we used a lock, other processes are forced to wait, which means that our process is now very, very slow. Now remember, the entire purpose of our URL shortener is to very, very quickly redirect short URL to long URLs. So if we make this process slow, then we have a very bad system. So once again, if we dig deeper and try to find a solution that does not involve locking, we can think once again of doing something in the database. In this case, we want to increment in the database. So the problem that we had previously is that we updated the hit counter based on the value we had in the application's memory, right? So this value can become stale when you have lots of transactions operating at the same time. But what if instead of setting the value, updating the value to an absolute value like 1, 2, 3, 4, what if we just stay to the database, take whatever value you have and increment it by 1, okay? So this is what it looks like in Django. It basically says update hits to whatever the value of hits is plus 1, okay? This is what the SQL looks like, okay? So instead of setting hits equals 2 or 3, we say hits equal hits plus 1, okay? So now we increment the hit counter relative to what the database has stored and not what we loaded into memory. So we now don't need a lock almost at all. It's very, very short lock. We have an accurate counter. It doesn't go out of sync. Other processes don't have to wait, so it's much faster. But the only problem that we have with this solution is that we don't have the latest accurate counter. So I'll be honest with you, this is fine. You can stop right here. This is a great solution, okay? That last point is extra credit, but we are going to see the solution for that as well. So the problem is that previously we loaded the short URL, and then when we incremented the hit counter, we updated the database, but the object that we have stored in memory now doesn't have the most recent counter. So maybe I fetched short URL, the hit counter was 10, and then I incremented in the database, and I returned this object to my client application. So at this point, I didn't actually know how many hits came in while I processed the request. So usually it's fine, okay? But if you really, really, really need to know what is the value after you update it, so what you can do is you can use the returning clause, okay? So Django doesn't provide this out of the box. Maybe other ORMs do, but this is what the SQL looks like. We update the short URL, increment the hits relative to what the database has stored for a given key. And then we want to return the updated data, okay? So now we don't even need to fetch the object. We immediately try to update it, and then we get the updated data as a result. You see that? So now if we didn't update anything, then it means that this short URL does not exist. And if we did, then we can just return the object. So that's a very cool trick, especially if you implement a lot of ETL processes or have lots of concurrency problems. So with this solution, no lock, accurate counter, no other processes don't need to wait, so it's faster. And you have the latest accurate counter. The only problem with this approach is that not all ORMs have built-in support for returning. For example, Django does not. So your call. So the last mistake I want to talk about, and I think that I have maybe a few more minutes left, is underestimating the chances of concurrency issues. So let me tell you what it looks like usually in a code review when someone says, hey, you might have a concurrency issue here. So the developer would usually say, what are the chances of two 6-character random keys to generate the exact same random key at the same time? Okay. So once you start calculating the probabilities, it's very tempting to just dismiss concurrency issues altogether and say, it would never happen to me. The chances are so slim that it won't happen. So to that, I would say, usually when you do the math, you assume that the load on the system is distributed evenly. But we all know that systems have peaks, they have seasonality. You have times where you have a lot of load on the system. You have times that you have less load on the system. So when you consider the peak hours, the math changes. Second, anyone that ever maintained a system in production knows that anything that could go wrong will go wrong. So if you leave something open like that in your code, you're bound to get a call in the middle of the night saying that some weird concurrency issue happened and you need to wake up right now and and fix it. So hopefully now that you know these patterns for handling concurrency, you can resist the temptation to dismiss them because of probabilities, okay? So just a quick recap of what we talked about. We created a short URL. We started by talking about the first mistake, which is failing to recognize possible collisions. And then we described the TOCTOU problems. The first solution that we went to is lock, because we always lock. And we said that while it solved the problem, it's very slow. So then we decided to go Pythonic and just ask for forgiveness. Remember, we utilized the fact that there's a unique constraint in the database. In the second use case, incrementing the hit counter, the mistake was to ignore race conditions. The first solution involved a lock. The second solution ditched the lock and instead incremented in the database. The problem there was that we didn't have the most recent value of the head counter. So we saw how you can use the SQL feature returning to actually update and immediately get the most recent object from the database. So takeaways. First of all, concurrency is mostly an issue with awareness. So once you realize that concurrency may cause issues, you can start looking at your code and ask yourself, what would happen if more than one process executes this code at the same time? Second, don't let probabilities distract you. You know how to handle concurrency now, so just do it. And third, when you do have a concurrency problem, locks is not always the solution, okay? It slows things down, causes contention. So we saw different ways of handling concurrency without resorting to locks. So you now have more tools in your toolbox. So that's it. Unfortunately, we can't see each other in the video, but you can check out my blog and this address. You can find me on Twitter. I tweet stuff about Python all the time. You can also find me on LinkedIn and tell me what you thought about this presentation. If you want to get stuff when I publish something new, you can subscribe here, or you can just send me an email saying that you didn't like the presentation. I'm totally wrong about everything. Okay, so thank you very much. I think that I'm right on time. Okay, thank you.
Yes, actually, thank you so much as well. But we do have a question for you.
Okay.
So, hopefully you can see that and you can answer that since we have little time. Should I read it for you?
Oh, okay, in the Q&A.
Yeah.
Let's see. What would we keep in mind when dealing with concurrency in a deployed web server? For example, forking processes cause problems with certain libraries. Is there a recommended model or deployment like single process multi-threaded? How do we make sure that forking processes doesn't cause unexpected issues? So that's a very specific question. It's very dependent on how you run your server. For example, you can run it with WSGI and then you have one answer. You can run it with GVents and then you have a different answer. You can just run async IO and then you can use threads. So that's a very specific question. I don't have a good answer for. Hopefully that's enough. But thank you for the question. I really appreciate the participation. Thank you.
Okay, thank you once again for your interesting speech, and I hope the audience is like also grab the best out of it. And thank you, Haki, once again. So hoping to see you next year as well. So yeah, thank you.
Thank you. Bye.
Bye. So we will be moving to our next topic afterwards.